So thank you very much for the presentation. Um, I am Marcelo Mendoza from Chile for the Department of Informatics in Universidad Técnica Federico Santa María in Valparaíso, Chile. And this work is about information retrieval and word embeddings. Um, well, the context for this presentation is information retrieval. That is a classical task and a classical area in computer science when you are trying to formulate a query to a query engine, trying to retrieve some relevant documents that are related to the query. But the main problem here is that the query, it only involves or includes just a few words. And then using these few words, you want to retrieve very relevant documents. So you have this asymmetry in information between the information that is involved or represented in a query and the information that you want to retrieve. So you want to retrieve relevant documents, and many documents ideally, but providing to the search engine very few information about your information need. So the query, in general terms, it only involves very few words, and not always it is very informative enough to retrieve these documents. So this is mainly the problem of information retrieval, the asymmetry between the information that is provided by the users to the query engines, to search engines, and the expectations that you have trying to retrieve relevant documents. So you want to retrieve relevant documents providing just a few words. So this problem is very difficult. It's very hard from the point of view of uh, the identification of relevant information. So in general, information retrieval systems works by providing a representation of the query and a representation of the documents. So in general terms, these representations are provided by vector representations. And we define some features to describe the content of the queries and the content of the documents. And roughly speaking, these features are generally related to words. So we use the words to describe the content of a document and the content of a query vector, trying to create a representation of these objects, the queries and the documents, using the words that describe the content of these documents and the queries. So the problem of ranking of documents, so this to provide to the user an ordered list of results, is addressed by using a scoring function. This scoring function provides the scores for documents related to the query. So the main problem is to try to align or to provide a good scoring function that being able to sort or to order these documents in terms of the relevance of the query and in terms of the relevance of these documents to the user that formulated this query. So this is a very difficult problem because to order a list of results is very difficult because you want to identify these relevant documents and to put these documents on the top positions of the list of answers. And this is very difficult because you not only need to identify relevant documents, you need to sort or to order this list, providing some additional information that will be useful to identify inside the list of results which of these documents are more relevant to the query. So it is not only the identification of the relevant documents, it is more than this. It is also related to to the ordering of this list of results related to the relevance of these documents to the original query. So you have two problems: the retrieval of the documents that are relevant to the query, and the sort and the ordering of these documents related to the original query. So representation learning, as you use query vectors and document vectors, representation learning, a very active area in deep learning, is strongly related to information retrieval because we can use different representations of words, for instance, to improve the efficiency and the efficacy, the success of these information retrieval systems. And representation learning is an area that is in charge of computing some representations that are informative for documents and for queries. But in general, they are also useful to represent images in computer vision and other kind of objects. So in general, representation learning defines some strategies that are helpful to define these representation vectors that are useful to compute some operations as the scoring of a document or the measure of the similarity between a document and a query vector. So representation learning is a key aspect of this presentation, and this is very useful, and our aim is to show you how important can be representation learning in terms of information retrieval performance. So the main idea is, by combining representation learning and information retrieval, is to use word embeddings that are vector representations of words to provide a better representation of the query. So if we have some word embeddings, one vector representation per word, we can combine these word embeddings, providing a better representation of the query. So the problem here is how to combine these embeddings to provide a representation of a query. So the most direct and simple idea is just to use the mean of these vectors, just to average the word embeddings, and then to get in the centroid of these vectors. And then we use the average word embeddings of the words that compose the query to create the query representation. This is a standard way to represent queries using word embeddings. And then instead of using the original query vector that can be computed using, for instance, TIF-IDF or some classical strategies to represent term vectors, you can combine word embeddings using then the query vector to compute the operations inside the search engine to retrieve relevant documents. This is the most standard way to compute a query vector, a query embedding, in fact, from word embeddings. And then if you have this query embedding, you can use this to compute the relevance of each of the words of a given document with the query vector. So you can use the cosine similarity, for instance, as a scoring function, and then you can measure the relevance of these words, of the document words, to the query. But the relevant point here is that as you have a representation in a continuous and dense space of latent vectors, you can compare this vector that represents the query with all the terms of all the words in the vocabulary, because you project the query into the same space of the word embeddings by performing this combination of word embeddings using the aggregation function. So the key point is that when you use word embeddings, you can compare the original query with the whole vocabulary of terms, because you are projecting the query into the same space of the word of the original word embeddings. So it is very useful in terms of recall for a search engine, because this comparison that now it is more straightforward, even that you are working on the same space, representation space, in terms of the representation of the original query and the words that compose the vocabulary, makes more easy to identify related words to the original query. So in terms of recall, it is very useful. So the point here is that this aggregation function that use the average scoring, it is given the same weight or the same importance for all the words, because you have a flat or a plain combination of the words, giving the same importance to each of these words to create the representation of the query. So our proposal is to use the idea that some words are more informative than others, to provide a more a better representation of the query, taking care of the way that we using to combine these word embeddings. So our idea is to use the inverse document frequency to combine the word embeddings, providing a query vector representation that is computed using the combination between these word embeddings according to the IDF values of each of the words that compose the original query. So the main point here is that IDF is a very good descriptor of the importance of a word in terms of information retrieval in an information retrieval system, because words that are more specific tend to have more relevant or high values in terms of IDF. So specific words will be more important for the representation of the query, and more general words, like for instance stop words or words that are of very general use, will be less important. So the intuition behind this is that the more specific words are more important for the computing of the query representation using IDF average word embedding. So this is the standard IDF scoring function, that is the inverse of the number of occurrences of the word in the documents of the system. So if this word occurs in many documents, it will have a very low IDF score. And if it is only used in a few documents, it will have high values in terms of IDF. So IDF measures IDF measures the level of specificity of a word in a system. And if we use IDF to combine the word embeddings, we can give more importance for the representation of the query to words that are more specific. The idea of the combination of these word embeddings is related to the translation of these vectors. And then if you divide by the sum of all the IDF scores, you will have a vector that will represent the original query. Mainly the idea is that that the norm of the magnitude of each of these word embeddings will be multiplied by the IDF score. So terms that are more specific will have a more relevant magnitude in this combination, and then it will provide a more information in terms of the composition of this query representation. This is the main idea. So we have two ways to work with our representation. The first is to use it as a term scoring, just replacing the average word embedding in the scoring function by our IDF average word embedding scoring function. The second idea is to use query expansion. As we have the representation of the query in the same space of the words, we can use this vector to identify related words. So it is possible to expand the original query, identifying close words to the new representation of the query, including these new words in the query to reformulate or to formulate a second query. This second query will be formulated into the search engines to retrieve new documents. And then the idea of query expansion drives to query to document re-ranking. So to the combination of the original documents that were retrieved when we used the original query, and the combination of this document with the documents retrieved using the expanded query. So the idea is to identify these new documents and then to combine these documents with the original documents using, so we will need to define this score function, combining the scoring function of the original queries and the scoring function of the expanded query. And we just propose a linear combination of these two scores, the one that is achieved using the original query, and the second one that is provided using the expanded query, the query that includes these new words that are close to the original, to the query representation. And as a base or basic model, we can use a traditional or classical information retrieval scoring function as, for example, BM25. And of course, we can also use as a scoring function for the re-ranking our IDF. So we have many ways to combine these results in our framework that is combining word embeddings using IDF scoring functions. And we also include an extension of Elmo that is word embedding that considers the context of a word to create a specific word embedding that is considering the context. And in this case, we will use each document as a context for each word embedding. In fact, we use a text window around each of the words that match the query and the document to create a context of each of these words to compute the word embeddings, considering this text window around the match of each of these words in the document as a context to compute the Elmo. So this word embedding in a specific, it can be useful to incorporate context to create query representations that are specific to each of the documents, because word embeddings will be conditioned on the documents that will be involved in the comparison between the query and the documents. So this is very important because using Elmo, we can obtain a specific query representations that are conditioned on each of the documents that are involved. But it will involve some computational costs because we will need to compute these word embeddings to create the query representation for each of the documents. So it is very expensive in terms of computational costs. But well, we will evaluate this in this paper to measure if it is important to use Elmo and to measure the impact of this in terms of information retrieval performance. So our experiments considers two classic corpuses that are included in information retrieval systems performance evaluation, that is the Wall Street Journal corpus and the Associated Press corpus. And we use some query relevance that are provided by Trek to evaluate the precision, recall, and the NDCG measures of our system. And we have many methods that we evaluated in our paper. So the BN25, the average word embedding, our proposal IDF average word embedding, and BN25 combined with automatic query expansion. And then we have the query likelihood model and the automatic query expansion combined with the centroid. So we have many variants of our of these models for information retrieval. And some of these variants are considers re-ranking, and some of them not. So just using one phase to order the documents, and when you consider re-ranking, you are considering the combination of two lists of relevant documents, a first list that is related to the original query, and a second list that is related to the expanded query. So we combine these approaches, and we evaluate these approaches using these corpuses. And we studied 5 word embeddings strategies: continuous bag of words, skip grams, globe, fast text, and Elmo. So we have many combinations. And the results are here. So basically, so we have many results in terms of precision, recall, and NDCG. So remember that NDCG is a measure of the quality of the order of the results. MAP measures the amount of relevant documents in the top 10 list of relevant documents. And recall measures the number of relevant documents that are included into this list of results, considering the whole number of relevant documents that are in the ground truth. So naturally, precision results are achieves better results in terms of the systems, achieves better results in terms of precision than in recall, because in recall you are measuring, comparing the whole list of relevant documents of the system. And we constrain this list to the top 10 most relevant documents. And some important results: re-ranking works well in terms of precision. So if you use re-ranking, you will improve the precision of the system with very good results So if we compare these results for both data sets, we can observe that IDF, average word embedding vector space, combined with this query expansion methods, in this kind, the automatic query expansion based on IDF centroids, combined with this fast text in specific, get the better results in terms of map in both datasets. But it is not so good ordering the results. So skip rams with average word embedding vector space, so the classical representation of queries combined with these skip rams, provides the better results in terms of NDCG. So NDCG is in the scale of 0-1, and map and recall, and is in this scale of 0 to 100. So 0.7 in terms of NDCG, it is very good results, being the best result achievable by NDCG, 1.0. So 0.7 in terms of NDCG, it's a very good results. So this result is showing to us that skipgrams and continuous bag of words are very good representations in terms of the NDCG measure. So skipgrams and SIBO, without re-ranking, are good to order the results, but not so good to identify relevant documents. So maybe the point here is that you are able to identify these relevant documents and to put them into the top position of the list. But you are unable to identify many relevant documents. This is the reason why you can achieve a good NDCG, but not so good results in terms of map. And on the other side, re-ranking works well in terms of mean average precision, showing that re-ranking and query expansion can help us to identify more relevant documents into the top 10 number of relevant results. So some results that are related to query expansion show that in word embeddings are very useful to identify relevant words or related words to the original query. So query expansion can be boosted using word embeddings, because it is possible using these representations to identify related words that enrich the description of the original query by means of the expanded query. So as a conclusion, I can say that word embeddings trained on the fly, I mean with these skiprams and SIBO that are static word embeddings strategies that do not consider the context, allow better results in terms of recall. And IDF, average word embedding vector space, gets improvements in terms of map, keeping good results in terms of recall. And query expansion techniques get improvements in precision at the cost of lower results in recall. And the combination of IDF, average word embeddings, with fast text gets the better precision results using a query expansion and re-ranking based on a BM25 baseline model. Why fast text works well? Well, because fast text is trained using the subwords. So it gets some improvements in terms of out of vocabulary problem, allowing to identify related terms to the original query that expand or address the main difficulties that are related to the mismatches between vocabularies of TREC and vocabularies of the external sources used to train or to pre-train these embeddings. So for example, Wikipedia or Google News that were used to train fast text and Grove, respectively. And word embeddings training to solve query document term mismatches can be helpful in information retrieval. So, thank you.